Let's discuss chapter number 4, discrete Fourier transform and signal spectrum. So what we are going to study in this chapter is how you can look at how you can find the spectrum, that is the frequency components associated with a time domain signal. In chapter number 1 or 2, we discussed the frequency spectrum of different signal. Actually, frequency spectrum of one signal, which is a sinusoidal signal that produces two impulses at the frequency of the sinusoid, at positive and negative frequencies of the sinusoid. Uh, and we also discussed when you're sampling the signal, how fast you have to sample such that you can recover the signal from its frequency components or from its spectrum. And that, of course, that limit is that it has to be sampled twice the amount of Nyquist rate, at least theoretically, to recover the signal from its sample. Now in this chapter we're going to start with the Fourier series, and then Fourier series will take us to discrete Fourier transform. And discrete Fourier transform is basically the spectrum of the signal, discrete signal, in the frequency domain. So let's start with what is Fourier series. And right now this is analog signal. So Fourier series, as I have discussed in other classes as well, any periodic signal, analog signal, can be decomposed into three components: the average value of the signal, which may be 0 or may not be 0 based on if the signal is symmetric about x-axis or if it is not symmetric about x-axis. So it may be 0 or may not be 0. If it is symmetric about x-axis, then it will be 0. That is, you have the equal area on the positive side of the x-axis as you have on the negative side of the x-axis. If those two areas are equal in one cycle, in one period of the waveform, then those two will cancel each other and your average value is going to be 0. But if those two areas are not equal, then you have some average value of that periodic signal. So that's one of the components. The other component is every periodic signal, no matter what is the shape of the periodic signal, every periodic signal has a sinusoidal component with the frequency to be the same as the original periodic signal. So if you have, let's say, a square wave with a frequency of 1 kilohertz, that square wave is carrying a sinusoidal signal with the frequency of 1 kilohertz in its construction when you create the square wave. So one of its component is going to be a sinusoidal signal with the frequency 1 kilohertz, and that component is called fundamental component of the signal. The third component, or the third series of components rather, are called harmonics. And what are harmonics? Harmonics are basically a number of sinusoids that have frequencies which are multiple of the fundamental frequency. So if your fundamental frequency is 1 kilohertz, you may have harmonics in the signal that you are analyzing at frequencies of 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, so on and so forth. And there are infinite number of harmonics in an analog signal theoretically. Sometimes you have a specific harmonic and the other harmonics are not present. For example, you may have only odd harmonics, 3, 5, 7, 9, so on and so forth, and all the even harmonics may be 0, 2, 4, 6. And sometimes it's the opposite of that. You may have even number of even harmonics and the odd harmonics are 0. So it all depends what type of signal you have. Again, we're not going to go into the derivation of Fourier series of different signals. That's not the intention in this chapter. Fourier series is just, I'm introducing Fourier series here because this is the basis of discrete Fourier transform in the discrete domain, in the digital domain. So again, to reiterate, Fourier series tells you that every analog periodic signal is comprised of three components: an average value, which may be 0, may not be 0, a fundamental component which will always be present, that is a sinusoid with the frequency to be the same as your input signal, and you will have some harmonics. Now, if it is only a pure sinusoidal signal, a tone signal, what we call it, then of course there is no harmonic, because that's the frequency of the periodic signal, which is the fundamental frequency. So if you have a sinusoidal signal, then the harmonic is 0, based on if you are offsetting that sinusoidal signal by a DC value. That DC value will be the average value of the signal. If you're not offsetting it with any DC value and it is symmetric about x-axis, then of course DC value of that sinusoid will be 0, and it will only be fundamental component that will be present in that periodic signal. But in general, if your signal is not sinusoid and it is periodic, as far away as you move from the shape of a sinusoid, you are introducing more harmonics in the signal. That's a general rule. Okay, so how do you mathematically define Fourier series? There are three ways to define Fourier series. And before we go there, I just put a little bit of some figures to show you that Fourier series of a triangular or sawtooth signal. And here, I'm not showing you the equation of that, but here basically I'm adding only 3 harmonics, or the harmonic number 3. So I'm adding, there's 0 for, let's see, yeah, there's a average value. So remember, the average value is the middle point. So this is the average value of the signal right here. So there's average value, there is fundamental component, and then I'm adding if there is a second harmonic present or not, because I don't have the equation over here, so I don't know if second harmonic is present. But I'm adding harmonics up to number 3, that is number 2 harmonic, second harmonic, and third harmonic, with the frequency of 3, and whatever the frequency of this waveform is. I don't remember when I executed the program what frequency did I choose, but it looks like it's 0.01, so 100 hertz. The frequency of this is 100 hertz. So this will have a sinusoidal component at the frequency of 100 hertz, and then I don't know if it has second harmonic or if it has only third harmonic, or vice versa, or both harmonics are present, but anyways. So this is up to harmonic number 3. And observe that the shape, although it looks like a little bit the triangular waveform or sawtooth, but it's still not perfect. Now you add the number of harmonics and you go up to number 13. And observe that it is getting a little better. Still there's a lot of noise over here, but it's still getting a little better. And then I went up to harmonic number 99, all the way up to 99. So I added the average value, I added the fundamental component, and then harmonics all the way up to 99. And observe that the shape is pretty much a sawtooth or a triangular waveform. So as many harmonics you are going to add, and depends on the signal as well. In this signal you have to go up to a very high harmonics to get a very cool triangular signal. In some signal you don't really have to go up to that many harmonics. So in general, when the number of harmonic is increasing, their magnitude is decreasing. So their contribution to the shape of the waveform is going down. Remember, theoretically it's an infinite series, but practically we just go up to the harmonic number where the harmonic is up to a threshold value. Let's say if you set the threshold value that any value of harmonic magnitude, if it goes below 0.01, then we will neglect it, because the contribution to the shape of the original signal or to the power of the original signal is going to be insignificant. So you're gonna go and look for that harmonic, and let's say that harmonic come out to be 15th harmonic. So all the harmonics above 15 are going to be neglected when you are analyzing the signal. So when you add all the components up to 15th harmonic, you should get your original signal back. So there are 3 different ways to express the Fourier series, analog Fourier series, and those 3 ways are trigonometric method to represent it, and then trigonometric method, the second is also trigonometric, but it's a compact trigonometric method, and the third one is exponential or complex Fourier series. So let's look at each one of them one by one.